This is SpaceTime Series 24, Episode 139. Coming up on SpaceTime, jets discovered erupting from the Milky Way's supermassive black hole, a new tool in the search for life beyond Earth, and a rare Antarctic solar eclipse. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have detected jets erupting from Sagittarius A star, the supermassive black hole at the centre of our Milky Way galaxy. Most, if not all, galaxies have supermassive black holes at their centres. Located some 27,000 light-years away, Sagittarius A star contains some 4.3 million times the mass of the Sun, and it's the anchor point around which our entire galaxy revolves. This monster has long been thought to be quiescent, that is, in a state of inactivity or dormancy, a sleeping giant. However, new observations by NASA's Hubble Space Telescope shows that this black heart of our galaxy still has some vestiges of its blowtorch-like jets. The findings, reported in the Astrophysical Journal, show that while Hubble wasn't able to actually physically image these streams of energy and matter, it was able to find circumstantial evidence showing the jets pushing into a huge hydrogen cloud and then splattering. This discovery provides further evidence that the supermassive black hole at the centre of our galaxy isn't a sleeping monster, but periodically awakens as gas and stars fall in. To physicists, a black hole is a point of infinite density in zero volume. As the name suggests, these points in space-time are so dense that nothing, not even light, can escape once it's passed a point of no return known as the event horizon. Material drawn towards the black hole by its immense gravitational pull forms an accretion disk spinning around the event horizon like water swirling around a drain before falling in. As this material swirls around the accretion disk, it heats up to millions of degrees. At the same time, it's being torn apart at the subatomic level, releasing huge amounts of energy and particles. While most will eventually pass the event horizon and fall forever into the black hole's singularity, some material is caught up in powerful magnetic field lines and then fired out from the black hole as perpendicular jets into deep space. These narrow beams are accompanied by a flood of deadly ionizing radiation. The study's lead author, Gerald Cecil from the University of North Carolina, says the black hole in the centre of the Milky Way is dynamically variable and currently powered down. Cecil was able to piece together a jigsaw puzzle of multi-wavelength observations using a variety of telescopes. Combined, they suggest that the black hole erupts with mini-jets every time it swallows something hefty, like a gas cloud or a star. Back in 2013, evidence for a stubby southern jet ploughing into gas near the black hole came from X-rays detected by NASA's Chandra X-ray telescope and in radio waves detected by the Very Large Array Radio Telescope in New Mexico. Cecil was curious to see whether or not there was a northern counterpart to these southern jets. So he first looked at archival spectra for molecules such as methyl alcohol and carbon monosulfide from ALMA, the Atacama Large Millimeter Submillimeter Array Radio Telescope in Chile. ALMA uses millimeter wavelengths to peer through the veils of gas and dust between Earth and the galactic core. The data revealed an expanding narrow linear feature in molecular gas that could be traced for some 15 light-years back towards the black hole. By connecting the dots, Cecil next found in Hubble infrared wavelength images a glowing inflating bubble of hot gas, which aligns precisely with the jet at a distance of 35 light-years from the black hole. Put together, the data suggest a jet from the black hole has ploughed into this bubble, inflating it. These two residual effects of the fading jet are the only visual evidence of it impacting molecular gas. As it blows through the gas, the jet hits material and then bends along multiple streams, creating a series of expanding bubbles extending out at least 500 light-years. Cecil and colleagues then ran supercomputer models of the jet outflows in a simulated Milky Way disk, which reproduced the observations. The work suggests that Sagittarius A star surged in luminosity, increasing by at least 1 million times current levels in the last million years, in the process producing a jet that punched into the galactic halo. Previous observations by Hubble and other telescopes found that the Milky Way's black hole had an outburst between 2 and 4 million years ago, and that was energetic enough to create an immense pair of bubbles towering above and below the galactic disk. These bubbles still glow today in gamma rays. They were first discovered by NASA's Fermi Gamma Ray Space Telescope in 2010 and have since been named Fermi bubbles. They're surrounded by X-ray bubbles first discovered in 2003 by the Rosat satellite and then mapped last year by the Rosetta spacecraft. Hubble ultraviolet light spectra has been used to measure the expansion velocity and composition of the ballooning lobes. The Hubble spectra later found that the burst was so powerful it lit up a gaseous structure called the Magellanic Stream some 200,000 light-years from the galactic centre, and gas is still glowing from that event today. To get a better idea of what's going on, CESA looked at Hubble and radio images of another galaxy which also has a black hole outflow. Located some 47 million light-years away, the active galaxy NGC 1068 has a string of bubble features aligned along an outflow from a very active black hole at its centre. Cecil found that the scales of the radio and X-ray structures emerging both from NGC 1068 and from our own Milky Way galaxy are very similar. The bow shock bubble at the top of NGC 1068's outflow coincides with the scale of the Fermi bubble start in the Milky Way. So, it seems NGC 1068 may well be showing astronomers what the Milky Way was doing in its major power outsurge several million years ago. This report from NASA TV.
Our Milky Way's central black hole has a leak. This supermassive black hole, over 4 million times more massive than our Sun, looks like it still has the remnants of a blowtorch-like jet dating back several thousand years. NASA's Hubble Space Telescope hasn't photographed the phantom jet yet, but it has helped find circumstantial evidence that the jet is still pushing feebly into a huge hydrogen cloud. This is further evidence that the black hole is not a sleeping monster, but periodically hiccups as stars and gas clouds fall into it. The hiccup results in superheated material blasting away from the black hole as narrow beams, or jets, shooting in the same direction as the black hole's spin axis, along with a flood of ionizing radiation. As the jet blows through the gas, it hits material, which creates a series of expanding bubbles that extend out to at least 500 light-years. The streams continue to percolate out of the Milky Way's dense gas disk into the galactic halo. Scientists concluded that the black hole clearly surged in brightness as much as 1 millionfold in the last million years. That would be enough for a jet to punch into the halo of material that surrounds the galaxy. Galaxy NGC 1068 shows a similar scenario occurring. Previous observations by Hubble and other telescopes found evidence that the Milky Way's black hole had an outburst about 2 to 4 million years ago that was energetic enough to create an immense pair of bubbles towering above our galaxy that glow in gamma rays. Hubble was used to see how fast the bubbles were expanding and what they were made of. Hubble later found that the burst was so powerful that it lit up a gaseous structure as far away as 200,000 light-years from the galactic center. Called the Magellanic Stream, this gas is still glowing from that event even today. The residual jet feature is close enough to the black hole that it would become much more prominent only a few decades after the Milky Way's black hole powers up again. Whenever that does actually end up happening, it's sure to be quite a spectacular show.
This is SpaceTime. Still to come, a new tool in the search for life beyond Earth, and Antarctica experiences a rare solar eclipse. All that and more still to come on SpaceTime. A new study warns that scientists really need to learn more about the chemical makeup of the Venusian atmosphere before they can start to speculate about the possibility of life in Venus's clouds. The apparent detection of phosphine, a chemical compound made up of one phosphorus atom surrounded by three hydrogen atoms in Venus's thick cloud cover, has sparked worldwide speculation in the scientific community about its implications for life beyond Earth. Could primitive single-celled microorganisms exist on Venus? After all, Venus and Earth are sister planets. They're the same size and mass. They were formed at the same time and in the same part of the solar system and out of the same material under the same conditions. So, if Earth has life, why not Venus as well? It's a tantalizing prospect. And the initial detection of phosphine, which is produced on Earth by bacteria, further fueled the speculation. However, those discussions were soon dashed when follow-up studies suggested that instead of phosphine, the signatures were more likely due to other chemicals associated with the planet's sulfuric acid clouds. Now, a report in the journal Frontiers in Astronomy and Space Sciences is providing new guidelines showing how an initial detection of a potential biosignature should be followed by searches for related molecules. The authors used computer algorithms to produce a database of infrared spectral barcodes for 958 molecular species containing phosphorus. Phosphorus is an essential element for life. Yet up until now, astronomers could only really look for one polyatomic phosphorus-containing molecule, phosphine. Phosphine is a very promising biosignature because it's only produced in tiny concentrations by natural processes. The study's lead author, Dr. Laura McKemish from the University of New South Wales, says the new database means when scientists look for evidence of life on other planets, they don't need to go to space. They simply need to point a telescope at the planet in question and search for specific chemical signatures, spectral signatures, of other associated molecules in the planet's atmosphere. However, McKemish says if scientists can't trace how it's produced or consumed, they can answer the question of whether it's unusual chemistry or little green men who are producing phosphine in the planet. The authors looked for which phosphorus-bearing molecules are most important in atmospheres, but it turns out very little was known. So, they looked at a large number of molecules which could be found in the gas phase, which would otherwise go undetected by telescopes sensitive to infrared light. Barcode data for new molecular species are normally produced just one molecule at a time, and that's a process which often takes years. So instead, the authors used high-throughput computational quantum chemistry to predict the spectra of 958 molecules within just a couple of weeks. Although the new database doesn't yet have the accuracy to enable new detections, it can prevent misassignments by highlighting the potential for multiple molecular species having similar spectral barcodes. For example, in some telescopes at low resolution, water and alcohol could look indistinguishable. This recent addition to the knowledge of what can be detected using telescopes will be important in the detection of potential signs of life on exoplanets, that is, planets in other star systems. Kemish says the only way scientists are going to be able to look at exoplanets and see whether there's life there is to use spectral data collected by telescopes, and that's where this new tool comes in.
Our particular bit of work was assuming if we had found phosphine, how would we understand what it had caused it? So was it biological, was it geological, things like that? And we proposed that you could do that by understanding more and trying to look for the molecules that it could be, aside from the molecules that could be present that could form phosphine and could be produced by phosphine. So I guess that's the bit of work that I led. But simultaneously, I think it's really important to recognise that since the original detection, there's been quite a few challenges, I think I'd say, to the detection. So people have queried the analysis technique and whether the signal, there was only one spectral line that was found for phosphine. So basically, you're trying to take a fingerprint to identify a person, but you've only got a really, really tiny portion of the fingerprint. And they hoped it was unique to phosphine, but you also had to check there was actually a fingerprint there, and there's some people, the astronomers, that have raised some concerns about that.
Yeah, they found that the section of the fingerprint they have was common to other molecules as well, including sulfur islands.
Yeah, I think sulfuric acid, look, I'll leave it to the astronomers to debate whether it's sulfuric acid or sulfur dioxide. Well, the important thing there is that there's a spectral line, and I guess it relates to the work that we did. There was one spectral line, and it can be attributed to phosphine, Some other people say that it might be a sulfur species because it's very, very close. But I think the important thing to recognise is that the number of molecules that we've got that really, really accurate data for is a tiny fraction of all the molecules that can exist in an atmosphere. So Earth has lots and lots of trace species. Venus is a really, really different atmosphere. So there might have been lots of different molecules there. And we only have data for a certain number of them. And if you don't have data, then you can't get anything.
So what did you guys do about this?
So what our research was about is producing approximate spectra, so approximate barcodes or fingerprints for a whole set of phosphorus-containing molecules. And we picked phosphorus as sort of our first example, but we're going to extend that research to other molecules and eventually produce approximate spectra of thousands of molecules. 16,000 is our current target. And the interesting thing here is that previously there's really, really high resolution data on probably less, 100 to 1,000 molecules, depending on what sort of data you're looking at, whereas there's no data on a whole bunch of other molecules. So we actually got some approximate data using a technique called computational quantum chemistry, which basically means we put molecules into a computer and then we solve the equations that describe the motion of electrons within that molecule and the motion of nuclei within that molecule, and then it gave us information about how that molecule absorbs light.
This acts like a barcode pattern. You can place it on an atmosphere and say, there are these points here which are common, and that indicates this sort of molecular compound.
Exactly. So in general, spectra is what we call them, basically a barcode, and it says that each molecule has a unique barcode which tells you which colours of light that molecule absorbs and at what intensity, and that changes as a function of temperature, and the amount that it absorbs obviously changes with how much the molecule is there. And currently we can only detect a certain number of species, but the paper that we wrote paves the way for us to detect many more species. It's not sufficiently accurate for many purposes, but what it is really good for figuring out even now is if astronomers say, I think we've found this molecule in an exoplanet or this molecule in Venus or a different planet, we can use our data to say, that's one molecule, here's some other options could be. You think the one done is most likely in the particular atmosphere. So it helps identify other potential candidate molecules that a particular barcode could be, and that will inform future speculation. So, for example, exoplanets, they've found HCN, but the spectra of acetylene is really quite similar. That's C2H2. And so it's a bit unclear to some people which one they actually found, and better data can help figure that sort of thing out.
And that's where your barcode comes in.
Exactly. So you need the correct barcode for lots of molecules in order to be able to find the molecules.
Now, this is going to be an important piece of software to have because with programs like James Webb about to come online, well, hopefully,
yes.
That's one of the things that James Webb will be looking at will be atmospheres in exoplanets.
Oh, amazingly, I think when James Webb was first hypothesized, I don't think exoplanets had been discovered yet. And now that James Webb is hopefully going to launch exoplanets and searching the atmospheres of exoplanets, the molecules, is one of the key science cases of the James Webb Space Telescope, and it will spend a lot of its time hunting for molecules in exoplanets. And part of my broad research is giving them the data that will allow them to do that. So one molecule I've studied in the past is titanium oxide, which just imagine titanium bonded with oxygen. And it's a really weird molecule to chemists, but to astronomers, it's really, really important in hot objects. But we give them a lot of this really, really accurate data. But the new paper that we've just published is about going, well, we've only given you data for a handful of these molecules. What if it's something else that we haven't given you really, really accurate data for? What if we give you an approximation just so you can check? I think an analogy might be a good way to think about it. So you've got fruits in a shop and you know the 10 most common fruits, an apple, banana, orange, and strawberry, and that's fine. But what if you have some unusual fruit because you're in the tropical environment?
And if you didn't know or something.
Yeah, exactly. And if you don't have knowledge about what a plantain looks like or what kiwis or what unusual fruits look like, you might look at some of these things and go, say if you didn't know what a lemon was and you looked at a lemon, you might go, oh, that looks fairly similar to an orange, so I'm going to call it an orange. But it's very, very much not an orange. And that's the sort of thing that there's a risk of with the James Webb Space Telescope. We might be looking for apples, so we find apples, but there might be unusual fruits that we don't look for, or unusual molecules.
You have the barcode. What about the sorts of things you're likely to find in the atmosphere of an exoplanet?
That's an excellent question. And I think to figure out what we're likely to find, we actually really need to use an interdisciplinary team. And we need to work with the people the astrobiologists and the people that are searching for the origin of life on Earth. And the interesting thing about this particular paper that we wrote was we actually got spectroscopists, experimentalists and computationalists, we got astronomers, we got geologists, we got origin of life experts and put them all together. And it was really insightful, I think, for everyone to understand what the origin of life, they've got theories about how life emerged. And actually one of the key questions is, how did phosphorus become bioavailable? So how did phosphorus get into our bodies? And phosphorus is one of the most important elements in our body biologically. It's actually really, really hard to get out of rocks. And when I was talking to the origin of life and the geologist people, what the collaboration did was allow us to take the next step and say, okay, how can we see that it's gotten out of rocks? How can we see it atmospherically? And how can we look at the atmosphere of a planet and understand what's going on geologically and what's going on chemically, and maybe start to understand the real origins of life spectroscopically, which is, of course, the main hope of the James Webb Space Telescope. Yeah, exactly. Look, we're going to be lucky if we get there, but that's one of the big targets, to understand if life was there, and if so, how did it arise, and is it similar to how life arose on Earth?
That's Dr. Laura McKemish from the University of New South Wales. And this is SpaceTime. Still to come, a rare Antarctic solar eclipse, and later in the science report, the artificial intelligence designed life form, which has developed a new, never-before-seen in nature form of replication. All that and more still to come on SpaceTime. The Antarctic has experienced a rare total solar eclipse, and it's given researchers a unique opportunity to learn more about how solar eclipses affect space weather. A total solar eclipse happens when the moon passes directly between the Earth and the Sun, covering the Sun's entire face as seen from Earth. Now, although the Sun is 400 times bigger than the moon, it's also 400 times further away. Usually the moon will orbit just a little bit above or a little bit below the Sun, and so you don't get a solar eclipse, or if you do, it's only a partial eclipse. But every now and then, orbital mechanics allows the moon's orbit around the Earth and the Earth's orbit around the Sun and the distance between the three bodies to line up exactly, so the moon appears to totally cover the face of the Sun, as seen from Earth. And for it to happen in either the Arctic or Antarctic is even rarer. For example, the next total solar eclipse in Antarctica won't take place until 2039. The thing you've got to remember about this is that during the Southern Hemisphere summer, the Sun never actually sets below the horizon. And so even when the eclipse took place, which was around 4 in the morning, the Sun was still present, although very low in the sky. The event was only visible in Antarctica, sweeping across the Ronny Ice Shelf in Ellsworth Land, with the rest of Antarctica in partial shadow. Total solar eclipses provide researchers with an opportunity to understand how switching the Sun on and off affects local space weather, the natural fluctuations in the space environment close to Earth caused by the Sun. Professor Mervyn Freeman and fellow scientists from the British Antarctica Survey used the event to measure changes in Earth's magnetic field caused by the total eclipse. They placed low-powered magnetometers along the alignment of the eclipse to examine variations in the Earth's magnetic field strength. These form part of a network of space weather sensors located at both polar regions and in space. Changes to Earth's magnetic field are caused by electrical currents in the upper atmosphere, and these currents are created by space weather, as solar wind particles streaming from the Sun slam into the Earth's ionosphere and magnetosphere. They then follow magnetic field lines down towards the north and south magnetic poles. And these are the same currents which generate the aurora borealis and aurora australis, the northern and southern lights. And while the auroral activity looks spectacular, they can also cause unwanted electrical currents in power grids, overloading circuits and damaging transformers. Scientists know solar eclipses change electrical currents in the upper atmosphere by increasing electrical resistance, but they don't fully understand how this happens. That's where this research comes in. They also want to see how changes to the Antarctic currents caused by the eclipse could indirectly affect currents in the Arctic, in the upper atmosphere, and even in space, affecting satellite navigation. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. China has launched a cyber attack against Australia, this one targeting 2 Queensland power stations. Had the hack been successful, it would have blacked out up to 3 million homes. The attackers tried to gain access through the power company's corporate computer system in order to reach generators supplying the grid with 3,500 megawatts of electricity. IT security technicians say the event was part of China's People's Liberation Army's efforts to test cybersecurity systems using a sustained ransomware cyber attack, tactics which Beijing will use during times of war. The attack was thwarted by countermeasures designed to separate the company's corporate and operational computer systems. Last month, China's cyber attacks targeted India's utilities and infrastructure sites, also trying to shut down a power plant. Last year, Beijing was also behind a malicious and sustained cyber campaign designed to infiltrate Australian banks, transport networks, hospitals, universities, crucial infrastructure, and the military. That followed earlier attempts to hack into federal parliament's computer networks. Just last week, Microsoft disrupted one Chinese hacking group which had carried out attacks across the United States and 28 other countries. And Taiwan says it's subjected to some 5 million cyber attacks every day, most of them from Beijing. Australia has seen a 15% increase in cyber attacks over the past year. That's roughly 1 every 8 minutes. Almost all of them originate from either China, Russia, or Iran. Scientists have used artificial intelligence-designed organisms based on living frog cells to develop a new, never-before-seen-in-nature form of reproduction. Called Xenobots, these computer-designed, hand-built organisms can self-replicate in the lab by manipulating loose cells together to form new multicellular organisms. Michael Levin from Tufts University in Massachusetts and Josh Bongard from the University of Vermont, together with colleagues, began extracting rapidly dividing frog embryo stem cells. The cells would naturally form ball-shaped clumps of around 3,000 cells within 5 days. The half-millimetre wide organisms were covered in minuscule hair-like structures that acted like flexible oars or flanges, which propelled the Xenobots forward in corkscrew paths. The authors then discovered that individual clumps appeared to work together in a swarm, pushing together other loose cells in the dish, creating new generations of Xenobots. However, initially the process only worked for a couple of generations. The team then allowed artificial intelligence to take over. It designed a C-shaped Xenobot that looked like a Pac-Man, which would gobble up the loose cells and then form them into new generations of Xenobots, which could then repeat the process over and over again for successive generations. Archaeologists have discovered the remains of a 2,100-year-old Hellenistic fortress in central Israel. The find includes a 2-story high structure with 7 rooms, a stairwell, weapons, burnt wood beams, and dozens of coins. The remains are located on a hilltop and are about 15 by 15 metres wide and some 5 metres high, and include sloping perimeter walls built from large stones some 3 metres thick. The site appears to have been part of a fortified line erected by the Hellenistic army to control the main road connecting the coastal plains region of Israel with the central highlands. Scientists say that based on the location and the archaeological finds there, the fortress would have been one destroyed by the Hasmonean leader and Jewish priest John Hyrcanus during his conquest of the region in 112 BCE, which is described in the Book of the Maccabees. The timing of the find was fascinating, considering Jews were celebrating Hanukkah, whose central theme is the Hasmoneans' defeat of Hellenists and the return of Jewish sovereignty to the region. To quote the immortal Dr. Sheldon Cooper, I know we do this a lot, but it's so good. There is absolutely no scientific evidence to support clairvoyance of any kind, which means that fortune-telling is a fraud, the profession is a swindle, and its livelihood is dependent on the gullibility of stupid people. And with that in mind, we report a 12-year study looking at thousands of predictions by so-called psychics, which has confirmed that they're wrong almost 90% of the time. The Great Australian Psychic Prediction Project examined some 3,800 predictions made between the year 2000 and 2020 by more than 200 well-known Australian psychics. Researchers trawled through magazines and newspapers, TV and radio websites, YouTube and the social media in order to compile the most comprehensive list of predictions possible. Tim Endham from Australian Skeptics says they found only 11% of all psychic predictions turn out to be correct, which when you think about it is even worse than simple guesswork.
This is the Great Australian Psychic Prediction Project. Started off by one guy within the skeptics, and it just gradually grew like topsy to involve a lot of other people. It looks at all those predictions that, quote, psychics, close quote, make at the start of the year, predicting what's going to happen in the next 12 months. Sometimes more than 12 months. Some of them go for years, etc., into the future. So we've looked at as many places and as many predictions as we could find, scouring libraries and this sort of stuff.
And this is more than just there'll be a major political disruption sometime this year. This is actual things you can put your finger on and say, Joe Bloggs will die tomorrow or something like that.
Well, that's the hard bit, actually, because we actually included every prediction.
Ah, right.
Over 3,800, so it's scientific, mate.
Yeah.
Over 3,800 predictions made by over 200 psychics over a 20-year period. Okay? No one, as far as I know, has ever done this before anywhere in the world. Certainly not in Australia, and I doubt if anyone's done it to this extent. It took 12 years of work on and off to actually gather this stuff. And the predictions of those 3,800 we had a panel of people who worked hours and hours assessing these, apart from collecting, also assessing these predictions, and they were classified according to correct. So actually say Bill Bloggs is going to die next Thursday and is going to be hit by a meteor, right?
Yep.
That could be correct, although there was none that was as clear-cut as that. And then there were others that were so vague you just couldn't even...
There'll be an earthquake.
Literally, yes. Yeah, that sort of thing, right? And then the people say there will be an earthquake in California. That's getting a bit more detail, but you say, yeah. So
there's one here every day.
That's the it's more than one, but that's the expected ones, right?
Yeah.
So the Blind Freddy could predict that one. That's the stating the bleeding obvious. Then there's the unknowns. You really don't know, how you can even find out whether something is true. It might be ultra personal. Nicole Kidman's going to have a ingrown toenail fixed up. You don't know. I'm not going to ask Nicole. And then there's those that are just wrong. Right, and that are just they made a specific prediction and it didn't happen. So drum roll. The end result is that out of these 200 odd psychics and 3,800 odd predictions, 11% could be classed as correct.
That's less than what you'd expect on a yes or no average, isn't it?
That's right. I mean, it's probably no better than guessing.
Yeah.
In fact, skeptics often do the same thing at the start, and we did this for one particular year, made a lot of predictions for a particular year, and we actually did better than that. We had some that were vague, perhaps they did it vague on purpose, but we had a higher percent correct rate, and we're talking correct, as in sort of stating something that can be say yes, did happen, and it's not pure guesswork. It's not stating the obvious. So, I mean, the wrongs were about 58%, or 50-odd% that were just flat out wrong. You said something specific and it didn't happen. So, if the old story is that if your car mechanic got it right only 11% of the time, you'd say, I'm going to find a different car mechanic. But if all the car mechanics only got it right at 11% of the time, you think there's something wrong with the car mechanic industry. Well, the same thing applies to the psychics. I mean, these people who make money out of their predictions and character assessments and that sort of stuff, they appear on TV and the TV stations ooh and ah over them and say, wow, that's amazing you made these predictions. But they never bother going back and checking. And skeptics being spoiled sports as they are, we went back and checked for a 20-year period. That's a big spoil sport effort, I can assure you. So you're not getting Bill Bloggs will be hit by a meteor on the 15th of July at 9:58 p.m. While walking around the city. There was nothing like that. Now, there's a whole lot of reasons that people might criticise the survey. We've covered all those. We've got a report in our magazine, The Skeptic, which is also available publicly, this report. And there's some obvious examples that people are going to use. The skeptics are biased, blah, blah, blah. If something was expected, then it should be correct. No, they are different things. All sorts of things like that we do cover, we do explain.
Sounds like you follow the scientific method in this pretty closely.
We tried very much. We're very concerned about it. Some predictions, when we were assessing them, would take hours to assess because you're there looking about, sort of how well a certain team performed during a year of a football competition. You've got to go back and check every game and that sort of stuff. So some of them took a long time to process to see if they were correct or not. Some were obviously incorrect. The most interesting thing is the things they didn't predict, like 2 Malaysian aircraft going down in the 1 year. Michael Jackson dying. And the things they did predict that didn't happen, like the Queen was supposed to abdicate about 5 different times over the last 20 years. Prince Harry would now be King Harry. We would have anti-gravity machines. All sorts of, the weird and the wonderful.
When I was at school, I was expecting to have a flying car by now, and still nothing.
Definitely hoverboards, yeah.
Yes.
The thing is, the psychics will make a lot of vague predictions and then some specific ones. And if a specific one comes true, even by chance, they will dine off that for the rest of their lives. It was a fairly scientific assessment done in a very, as unbiased a way as possible. We think we found every prediction. There's probably bound to be some others out there that we haven't found. And we've looked at these claims, assessed them closely by a panel of people over a long period of time, and the result is 11% could be classed as correct. And that's not enough to actually build an industry on. Now, there's some of the psychics coming in saying, well, we don't really predict. We're actually there to help people. So, yeah, okay.
Of course, they
run away from the results. Yeah.
Relieve them of their money.
Yes.
What sort of reaction have you had among the legitimate community about this?
It's been mixed. I mean, obviously, there's a lot of people out there who believe in psychics, but there's a lot of people out there who say, yeah, it's stating the bleeding obvious to say that psychics can't do it. But, yeah, this is stating the bleeding obvious.
Documentation which has figures and reports in it that actually provides the evidence. That's the key thing here, isn't it?
That's right. Hard numbers.
Yes.
So it's not just a feeling. I know from anecdotally that psychics don't work. This is hard numbers, hard research over a long period of time, as comprehensive as possible, as far as we know, and never been done before. And that's it. The numbers are there, mate. And in this case, the numbers don't lie.
That's Tim Mendham from Australian Skeptics. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.